Wanted to talk to you a little bit about some engine lubrication pieces that can be a little confusing the first time around. We're going to focus on filters and oil cooling systems. So let's get started here. This should be a familiar diagram. This comes from the 8083 textbook, and I wanted to point out a couple features that we see in this diagram and also the purpose of a few things that we're looking at, just as a little bit of review. First of all, we know that we have oil coming from the oil sump or from the oil tank that is being pumped through and given pressure by our oil pump. The thing to notice about this oil pump is a gear type pump. It is a positive displacement, high pressure, low volume pump, meaning we are putting oil out at a high pressure but not necessarily moving a large quantity of it relative to other styles of pump. Additionally, it is positive displacement, which means it does not change the amount of oil that it will pump through. The only thing we can do to alter its throughput is to change the speed at which it is rotating by changing the engine speed. This will become important as we take a look at the purpose of our relief valve right here. The other component we have is our bypass valve, which is linked to our oil filter here, and then our outlet to the rest of the engine. I want to start by taking a look at the relief valve. The relief valve exists because we have to regulate the oil pressure within the system. If we do not, we can potentially cause damage to the system further downstream, where high oil pressure could potentially blow out seals or cause damage to other areas. The way that this is regulated is by this relief valve. Now, in this case, the relief valve has a tension spring which is being held under tension by this adjustable screw. This adjustable screw allows us to change the operating oil pressure of our system. Effectively, as oil is pumped through, any excess pressure will return to the inlet side of the pump by means of, when we reach a certain pressure, this relief valve will open up, allowing oil to return to that inlet side. With most wet sump systems, this return from the relief valve is simply going to go back into the oil sump. With dry sump systems, this is typically going to send oil back to the inlet side of the pump by means of a single contained chamber rather than sending it back to the oil tank. With other systems, we don't have this adjustment spring to be able to make adjustments to our operating pressure. Instead, what we have are washers that are stacked underneath this plunger on the spring to regulate the tension of that spring, thereby changing the unseating pressure it takes to allow oil to go into bypass through that relief valve. The second portion we're going to look at is our bypass valve. This bypass valve exists to allow oil flow to continue if this oil filter becomes clogged. This is an important thing that we have, and it's really a last option for us. Ultimately, the reason this bypass valve exists is because having an engine operate on dirty oil is better than having the engine operate on no oil pressure. So should this oil filter become clogged, this bypass valve, when pressure builds up, will unseat and allow unfiltered oil to flow down to the rest of the system. Now let's take a look at the oil filter itself. In this case, this is a little bit different than what we might see with a traditional spin-on or cartridge filter setup, the way that it's depicting the oil coming into the filter through this side housing. However, one thing is consistent, which is the flow of oil. When we filter oil, typically we're filtering from the outside in, meaning we have oil entering a chamber just outside this filter element in this area here, and then it passes through the filter element. This has the effect of causing the sediment that may be in the oil to fall down to the bottom of the canister and leave this element clear to continue filtering. The other portion that we see here is our anti-return flow valve that's incorporated to the oil filter. Effectively, what this is going to do is when the engine is shut off and the oil pressure is gone, it's going to prevent the backflow of oil from the engine to drain out of the filter, drain back through the oil pump, and drain back into the sump. This is important because once an oil pump is primed, meaning we've forced oil through the passages and forced the air out, you need to keep it primed. If we drain oil back out, then we may not be able to get oil pressure to build up again until we force oil back into that chamber. This has something to do with what we call draw length. Namely, if we have a gap of air between our pump and wherever the source of that liquid is, in this case oil, If that length is too long for what the pump can draw through, we are not going to be able to draw a good head pressure of oil through the pump and supply steady oil pressure flow through the rest of the engine. So we can effectively wind up with a dry operation if we aren't careful to pre-oil the engine. The other thing I want to point out to you is in a normal system, what we see with our oil filter is typically the pathway for oil to flow is going to come in and exit on the same side. What I mean by that is in a normal system, rather than what you see on the side over here, oil is going to enter through drilled holes that we see located around a central point on that oil filter. That will bring the oil outside of the filter element and force it through. Then when it's filtered, it is going to be forced up through a threaded portion that connects down to the oil galley that's on the engine. This is most typically what we see with spin-on filters and commonly what we see with cartridge-style filters as well. The other thing I want to point out here is when we talk about oil screens, this really has a lot to do with what we mean by full flow and non-full flow oil filters. In this case, the reason we would refer to this as a full flow system is because 100% of the quantity of oil being pumped through this oil pressure pump is going to be forced through the oil filter and into the engine under normal operation. If we go into bypass, then it could bypass the filter. But in normal operation, we force all of our oil supply through this filter before it can go to the rest of the engine. In what we would term a bypass flow or partial flow system, it's really an older system we don't see very often, and part of it has to do with the fact that the filtering systems we used weren't that fantastic. With oil screens, the application we see for them now is typically going to be to protect the inlet coming from the sump or coming from the oil tank so that we don't get any large chunks of debris into the pump that could cause damage. Typically we refer to those as rock screens. You may hear the term used. And if you work with radial engines at all, usually the running joke is those screens are only filtering enough to stop anything that has a part number on it still. So only large chunks of debris. It doesn't do a good job of filtering the finer particles. As a result, the system that they used, because the filter wasn't doing that much anyway, only about 10% of the oil flow through one of those screens would be only 10% of the oil flow would go through that screen. The remainder would just be pumped directly into the remainder of the engine without being filtered first. But again, the screens weren't doing all that much. With our modern filters that we see now, these elements are very, very nicely designed and they provide a very high level of filtering. So a lot of the things that would usually be entrained in oil that could cause damage, silicon, carbon, things like that could potentially damage bearings, has a tendency to get into valve guides, which can cause stuck valves, or valves don't seat all the way during operation. A lot of that is solved by using these better filtering materials and a full flow system. What I want to show you next is the two most common types that we're going to see. Now, far and away, what you're going to see most often dealing with piston engines is going to be this spin-on style filter where everything is encapsulated in a single unit. Its distant cousin over here is the cartridge style filter, where we have a separate filter element that can be replaced and the remaining housing is actually a part of the engine. Fundamentally, both of these filters are going to operate in the same fashion, just the spin-on filter is a little more convenient, and in a lot of cases the filtering elements are a little more robust than we may see with the other style filters. Most often you won't see these with oil systems as much as you'll see them with turbine fuel systems and hydraulic systems where we use a replenishable filter element like this. Again though, the flow that we talked about is very similar. Under normal circumstances, we're going to flow up through those drilled passages that are outside of this threaded portion we see. The oil is going to be forced through the filter element into this corrugated center, and then it's going to flow out through that center portion, which is screwed onto the engine. Two things I want to point out. This corrugated center is important because it keeps the filter from collapsing. And the reason that's important, the best way I can try to illustrate this is if we use maybe a coffee filter as an example. If you put a coffee filter in your coffee maker, you know we have that neat little cone shape, but ultimately the only filtering we have is just a single layer like so. So we have grounds on one side and water, and then it flows through and comes into your coffee pot. Now the way that this normally works is we have our single element, and our liquid can flow through that single layer element just like so. It does a fine job filtering. The problem is that this design does not allow us to filter a high volume of liquid that's coming through it, or a high volume of sediment that could potentially be trapped, especially with the flow requirements we have for a lubrication system. So what we see used most commonly is a trick that we use with a lot of different mechanical structures to try to increase the amount of surface area we have, but keep it within the same size constraints. What I mean by that is if we take this measurement from end to end that the filter is going to be taking up, we can fit more filter into the same space by corrugating it or pleating it, depending on the term you want to use. But by making all these pleats, we have the benefit of fitting a whole lot more filtering area or surface area to do the job of filtering into the same size constraints. And that's what we do with these oil filters. And it's the same trick that we see used with radiators and oil coolers, where by creating additional surface area to exchange heat, we can create a larger cooling area in the same physical size that we're dealing with. Last thing I want to point out to you with this filter is with most spin-on filters, what we see is a bypass valve that is integrated into the filter itself. Typically, the form we see this in is a spring that sits up here at the top of this filter. Typically, the filtering element that's inside will look very similar to the filter element that we see in a cartridge style, except it's all integrated into a single piece. The way this works is once upon a time, we would have a little flap here that would allow oil pressure to push in if the filter became clogged and then force its way through unfiltered. What happens more often is this spring up at the top is going to produce resistance against that entire element. And as pressure builds up, when we reach a point where pressure builds up high enough because this element has become clogged, it's going to force this entire filter element up against the spring and allow our oil flow to bypass underneath the filter and come straight out into the system so that we have unfiltered oil passing through. The last piece that we'll have integrated into one of these is our anti-backflow valve, which is usually going to take the form of a silicone collar that sits on these little inlet holes that are on the bottom of the filter. So when the engine is not running and we have no oil pressure, oil cannot backflow and drain out of the filter, taking sediment with it into the oil pump or anything like that. But when we have oil pressure, it is going to come forced up and it will force that little one-way valve out of the way and allow it to flow into the filtering element. Again, it's fairly simple with the mechanical devices that we're using, but a little bit tricky maybe to understand on your first time through. So I want to talk to you next just briefly about oil coolers. One of the things that is important to remember with an oil cooler is that we produce a lot of heat with a reciprocating engine. We would classify it as a heat machine, which means we take fuel in the form of, in this case, gasoline, we ignite it and we generate heat, and we extract that heat energy to produce the power that the engine makes. Now, one side effect of that is that reciprocating engines are not particularly efficient at converting that heat into usable energy. So a large percentage of that heat, and I'm talking 60 to 70% or more, is being lost and is not used to create any work that the engine is producing. When we have a liquid-cooled engine, we have engine coolant that circulates through and takes that heat away from particularly hot areas like the cylinders and cylinder head and moves it out to a radiator where it can exchange that heat. In the case of an air-cooled engine, we use lubricating oil, which can absorb that heat through contact with critical components inside the engine and take it out to an oil cooler where it can exchange that heat with airflow very, very similarly to the way that a liquid-cooled radiator would. What we're looking at here is a very unique setup that we see on the front end of the Focke-Wulf 190. This is a BMW 801 radial engine. You heard me right, BMW, good old Bavarian Motor Works. They were building aircraft for Germany back in the 40s. This is a very, very interesting setup that we see. This radial engine is very high output in terms of power related to its size, and it requires some special elements for cooling. This oil cooler ring is actually a very ingenious design. What you'll notice is that this entire cowling section here is very, very tight fitting and relatively small compared to a lot of different radial engines and the nacelle setup that they use. One of the reasons this was done was to provide better visibility for the pilot over the front of the aircraft and to reduce the overall size. I'll draw a picture for you that shows you how this comes together, I should say, but it's very interesting the way this functions. What you will see around this perimeter are attach points for a armor plate which sits right in front of that oil cooler. Now let's take a look at how this is going to function. So as we look, here's our nacelle portion right here. We have our oil cooler ring, which goes all the way around the front end of the engine nacelle there. And then we have the armor plate, which sticks right over like so. Now I've drawn that with a gap intentionally because there has to be a gap between that armor plate and the nacelle of the aircraft there. The reason being is there's actually an induction fan that sits right up at the front of the cowling. As that rotates, it helps to force cooling air in through the front of that cowling towards the engine, where it can flow past the cylinder heads and the cutout fins on the cylinder barrels to take away heat. As it's forced through, it actually builds pressure inside this nacelle section and forces the air to flow reverse up towards the front. That reverse flow forces the now heated up air to go through the oil cooler. The thing that regulates how much cooling is done is this little armor plate up at the front. There's a gap set, a special shim is used to change the separation there, and as airflow comes through the oil cooling ring, it exits out through that gap at the front of the nacelle and allows the now superheated air that has absorbed heat from the engine and the oil cooler to flow away from the aircraft. It's very ingenious in the design it has, and it's pretty clever, but it serves as a nice segue to talk a little bit about the functions we have for being able to regulate oil temperature and thereby engine temperature of a reciprocating aircraft. What I want to take a look at next is a common device we see. One of the beauties of having an oil cooler is, especially in a dry sump system, we can locate it remotely from the aircraft, or rather from the engine. So what we're looking at here is a Tiger Cat. We have a engine nacelle over here with a Pratt & Whitney R2800 inside, and the fuselage is over on this side. And this large scalloped opening right here is where the oil cooler lives. So the oil cooler is actually recessed just a bit in here, but this ducting helps to force ram air from the outside into that oil cooler. And then there's doors on the back that can regulate how much air is flowing through. Again, the reason that that's advantageous for us is we get it away from the engine, which is producing a lot of heat, and we can get it into an area where it's going to see a lot more airflow, so we can have a greater cooling effect through that oil cooler. In case you're wondering why this is such a strained picture with as dirty as it looks here, this is one of the few times in my life I've had to deal with a bird strike. We had a seagull or something that came. I believe the pilot was on the takeoff climb, and the bird came through the left prop section. As far as I can tell, it was dispatched on the prop, and then what was left ended up striking the leading edge of the aircraft here. Only time I've dealt with a bird strike, but one of the hazards of the job, I suppose. Kind of a odd and gnarly story. Anyway, moving on. What I want to show you here is something that's very similar, or at least more similar to the type of remote oil cooler that you see depicted in the 8083 textbook. So what we have is a Curtiss P40, and up here we have two radiators, and we have our oil cooler, which are allowing airflow to come through and mix that in with the oil that is flowing through very small passages transversely through the cooler. And then at the back, what you can see just to the back here is the tip of the flaps, which are regulating the amount of air that is flowing through these portions of the radiators. So we can regulate the amount of airflow by changing the position of these flaps to provide more or less cooling. The reason that's important is what we'll take a look at in our next slide here. So as we see, what we have here is this same oil cooler torn apart. We have a cross-section view of it here. We have oil that comes in from the engine, and we have a couple pathways for that oil to take. We have our control unit, which is mounted on the oil cooler itself, which is going to regulate flow through the cooler, and it's also going to regulate the amount of cooling that's imparted to the oil. It does this by changing the flow. We have this bypass jacket that goes around what we would term the core of the cooler. The core of this cooler is where we have oil that's forced through all of these little maze-like labyrinth passages that forces it into contact with airflow that's coming through the front of the cooler. By doing that, it allows us to remove heat from the oil by conduction. So by physically touching each other, we can transfer heat in that fashion, and it helps to take that heat away from the oil, away from the aircraft and the engine. If we change the amount of flow through this core, then effectively we can change the amount of cooling that is offered to the oil. There's a couple devices that we use to regulate that, and we'll take a look at that in just a second. If we do have one pathway for it to pass through, if we want to provide less cooling, then we have to have a way to avoid traveling through this cooler core or radiator core in the center, and that's why we have this bypass jacket. That is an alternative pathway for oil to take in the event that it is too cold and we don't want to cause that additional cooling by passing through the core of the cooler. So let's take a look at this from a slightly different view. This is a functional schematic of what we see with an oil cooler of that design in a couple different conditions. We're looking at a surge condition, cold oil flow, and hot oil flow. Now, there's a point of delineation that we need to make between our surge and cold oil flow. One of the things that happens, and we understand this with how lubricants work, the colder a lubricant is, or the colder a fluid is, the more viscous it becomes, or the more resistant to flow. This has to do with the laws of states of matter. We know that as something gets colder, for instance water, it'll eventually start to increase in viscosity until it is frozen. We don't necessarily have to worry about freezing with oil, but we do have to worry about that relationship between temperature and viscosity. This is really the reason that we have temperature regulation to begin with. The reason for that is, as the oil starts to heat up, it becomes less viscous and becomes thinner. One of the jobs that lubricating oil is supposed to do is provide a cushioning layer between metal parts that are absorbing a lot of force or impact from the byproducts of this combustive cycle. If that oil becomes too thin, it can no longer provide that cushioning support, and it can allow metal components to come into contact with each other. The other problem that we have is when oil is too cold, it becomes much more viscous. And the issue with that is if we were to force very cold oil through this bypass jacket or through the core of this cooler, then it could potentially blow out a portion, cause the metal to fail, and we now have an oil leak coming out of the cooler. So for that reason, we have a surge valve which has been installed in this control unit. The way this works is fairly simple. We have a calibrated spring, just like we would see with a pressure relief valve or with a bypass valve. And when the oil is very, very cold and thick, we produce enough pressure coming off of our scavenge pump that it forces this plunger up against the spring pressure. This is connected to a poppet valve that seals off this bypass jacket. So as we build up enough pressure on this side, it forces this up. It gives us another path for oil to flow, as depicted by this pink dotted line, but it also shuts off our bypass jacket, so we do not get any additional oil flow that goes through that bypass jacket, potentially causing damage. As the oil starts to heat up from that surge condition, we start to relieve some of the pressure on that spring, which thereby seals off this additional passage and now allows this poppet valve to open. Now, the key thing to remember is the oil has not become warm enough to reach operating temperatures yet. We are in a cold oil flow pattern, which again, if you follow this pink dotted line, shows that the majority of our oil is flowing through this bypass jacket and past our temperature control valve. You'll notice that this does not have a movable valve that closes off the core of our cooler. When we're in a cold oil flow state like this, it really doesn't cause us a problem because we've created an easier path to ground, or a path of least resistance, for this high pressure oil to flow through. So just by natural physics, it is not going to apply much pressure to the core of the cooler. Instead, it's going to take this easier bypass and flow back to our oil tank. The last piece we have is when we finally start to regulate oil temperature, and this really has a lot to do with our temperature control valve that we see in both instances. Now, I want you to listen very closely to this part because it's something that people get confused a lot when they're taking tests on this and when they try to troubleshoot problems with oil cooling systems. This thermal control valve is operated by heat. So the way that metal acts when it starts to heat up is it starts to expand. When it starts to expand, we move the position of this valve. So when the oil is cold, this valve is in its open position, which means it is not blocking off this bypass valve, or this bypass path, and so it allows oil to bypass easily. As it starts to heat up, it reaches its closed position. So when it reaches its fully closed position, it now prevents any oil from bypassing through this bypass jacket and forces all of the oil to flow through the core, where it can exchange heat with the surrounding air that's flowing through it. The last component that we see in this control unit is our check valve. And this check valve is only there to prevent oil from backflowing from the oil tank into the cooler and potentially back into the engine, where we could flood the engine with oil and cause damage. So when there's no oil pressure, this poppet valve is seated against the bottom portion here, like we see in this diagram here. As soon as we start providing pressure flowing through the cooler, then this poppet valve unseats and allows normal flow through it. Last thing I want to talk to you about is our other method of regulating oil temperature. With a lot of small aircraft, we have just an oil cooler and a thermostatic control valve, in some cases referred to as a vernitherm, that is going to be providing most of our temperature regulation. But in very high output engines where we produce a lot of heat, we need additional methods to be able to regulate the temperature of that cooler in order to match the different ranges that we're going to be operating in. So as a nice example of this, I want to direct you to the P51, and we're going to take a look at this lower cooling portion, this scoop that's on the bottom of the aircraft. Now we have cold air that is forced into this ram inlet here, and we have two areas. We have our oil cooler, which is parked right up front here. It's relatively small. And then we have our engine coolant radiator, which sits right behind it in what we call the doghouse back here. Now, interesting to note, this has two styles of cooler. We have a coolant or a radiator that's parked back here, as well as our oil cooler up front. So we have cooling being achieved from two different directions. The one thing you'll notice here is this little door that's on the bottom of our scoop. That is specifically for regulating the amount of airflow that can pass through that oil cooler. Again, this is all done by contact, so depending on the amount of air that we allow to flow through this housing, combined with the amount of oil that we're forcing to flow through the oil cooler, we can regulate the temperature of the oil fairly accurately. Similarly, the radiator has its own door at the trailing edge here, and that will regulate airflow through the radiator. And in the very same fashion, we can regulate how much cooling we're receiving through those two fixtures. Kind of an interesting aside here. There's a bit of an urban legend that says that this whole scoop arrangement on the Mustang actually produces a measurable amount of thrust. I don't know how true this actually is, but the science seems to be reasonably accurate. As we take cold air into this ram scoop here, that air is heated up by taking heat away from the oil cooler and the radiator, and it can become fairly hot. Now, because this door changes position to regulate airflow, it can actually supposedly act a little bit like the nozzle on a jet engine as a convergent duct. So we have cold air that comes in, it gets heated up and expands, and then is forced through a convergent duct, which theoretically should produce an additional amount of thrust. Now, whether that's measurable, who knows? But there's one of those little urban legends from the Reno air races that you can tell your friends about and see if they believe you. So as we talk about the position of these cooling doors, I want to touch briefly on our floating control thermostat. This is an analog device. It's an older device. Most newer aircraft are going to use a more complex system than this for regulating the position of cooling doors. But in all reality, that door position can be regulated from something as simple as a manual control in the cockpit all the way out to a fully electronic system that's taking multiple readings and adjusting how this operates. But the very basic function of this is we have a bimetallic strip up here which is pinned to and wrapped around a control shaft. When we talk about a bimetallic or bimetal element, we have two different kinds of metal that are placed together, and they're going to expand and contract at different rates due to different thermal coefficients. So this has the effect of, as we start to heat up, this bimetal element is going to expand, causing this shaft to rotate. As it cools down, it's going to contract, which causes the shaft to rotate the other direction. This shaft is controlling this contact arm in the middle. So up at the top and up at the bottom, we have two contacts, and you can see the power inlet that we have coming from either side. This is controlling the direction of motor operation for the motor that's controlling the door. So as we start to heat up, this shaft, this bimetal element is going to expand, causing the shaft to rotate, which is going to force this little arm to come into contact with one of these contacts. When it makes contact, it's going to complete our path to ground and allow that motor to operate in one direction, which will open the cooling door more until our temperature starts to drop. The bimetal element changes position, and this control arm goes back into its position in between these two contacts when it's regulating the temperature correctly. On the other hand, when the temperature starts to cool down too much, this bimetallic strip is going to contract, causing the shaft to rotate the other direction, which will bring it into contact with our other contact, operating the motor in the reverse direction, which will close that door further and regulate the amount of cooling that we receive. Normally, if it's happy with the temperature, this arm is going to float in between these two contacts. Usually these are not adjustable, at least by a mechanic, so you cannot take a unit from one aircraft and use it with another aircraft of a different type, because this may be set up to regulate for a totally different arrangement than we would see with another aircraft. It's going to regulate at a different temperature, so it may not give you the temperature you're looking for. The way that this works is it works with a simple electrical circuit. So in this case on the Mustang, up here on the left side of the panel where the pilot's arm sits, there's two switches, one for coolant and one for oil. And each switch has three positions. We have open, closed, and automatic. So open and closed, pretty self-explanatory. That is going to be our manual operation to either open or close the cooling door. When it is set into automatic, then it allows this floating control thermostat to regulate, or rather self-regulate, the position of the cooling door to maintain a set temperature for the oil or the coolant. That's the quick explanation on how this functions. I hope this has helped you out. I hope it helps you understand a little bit more about what we're looking with some hard to figure out concepts, at least at the first go at it. If you do have more questions, please post those questions onto our discussion forum that we have for this week's curriculum, or by all means, send me a message and I can try to help you out a little bit further. Thanks for watching. We'll catch you next time.